Hello everyone. In this video, let's learn about a multiplexer. A multiplexer or data selector, abbreviated by MUX. It has a group of data inputs on this side and a group of control inputs denoted here at the bottom. And all multiplexers have one output. So the group of data inputs and the group of control inputs are related by 2 to the power n. So let's call the data inputs here, this group, let's call them I. So I is equal to, and then n we called it for the control inputs. So usually I is equal to 2 to the power n. So for example, for 2 to 1 multiplexer, so we know we have two inputs and one output. Let's call this I0 and let's call this I1. So how do we know how many control inputs we need? So let's apply this here. So I is the number of inputs is equal to the power n. N is the number of control inputs. We know I is 2, we have two inputs, so let's 2 is equal to the power n. So that means n is equal to 1 to make this equal. So that means we have one control input. Let's call it C. How about 4 to 1 MUX? So let's draw the symbol for it. So 4 to 1, we know we have four inputs and they all have one output. So this is the four inputs. One. We know we have one output. Let's call this Z. So how many control inputs we need here at the bottom? So also we can apply this here. So I, the number of inputs, is equal to the power n, and n is the number of control inputs. In 4 to 1, I is equal to 4. So 4 is equal to the power n. So now to make this equal, we know n, it has to be equal to 2 to make 4 is equal to 4. So in 4 to 1, we need two control inputs. We can call them A, B, or anything. It's fine. So similarly, 8 to 1, let's see 8 to 1 MUX. So let's draw the symbol for it. We know we need 8 inputs, and let's call them I0, I1, and then we know we have one output. Let's call it Z. So how many control inputs we need? Also similarly, we can apply this. So we have I is the number of inputs is equal to the power n, and n we denote it as the number of control inputs. In 8 to 1 MUX, the number of inputs is 8 is equal to 2 to the power n. So in this case, we know n must be equal to 3 to make 8 equal 2 to the power 3, which is 8. So in this case, we know we need 3 control inputs. We can call them A, B, and C. Okay, so now let's look at the 2 to 1 MUX, get the characteristic equation for it, and draw the circuit. So 2 to 1, as we said, it has two inputs and one control input, we called it A, and one output, we called it Z. So if A is 0, I0 will be passed to the output. If A is 1, the control input, I1 will be passed to the output. So let's start by the truth table for it. So we have a control input, we called it A, and here we have the output, we called it Z. So if A is 0, A could be 0 and could be 1. If A is 0, we will pass I0 to the output. If A is 1, we will output I1 to the output. So from here we can conclude that Z is equal to, since A is 0, so this will be A bar or A prime multiplied by I0 plus. From this row here, A is 1, so this will be A multiplied by I1. And obviously from here we can see that if A is equal to 0, then this will be gone, and then we will pass I0 because A bar is 1. So we will get I0. How about if A is equal to 1? If A is equal to 1, A bar will be 0, so we will pass I1. Now let's see how we can take this and draw the circuit. So we have a summation. That means we need an OR gate, and then the output is Z. And then here we need A prime multiplied by I0, so we need an AND gate. And also we need another AND gate for A multiplied by I1. From this one we have I0, and then from this one we have I1. And also what we need A and A bar. So this is input A, and then on this side we can have a NOT gate. So for this AND gate we need A bar, so this will go here. And also for this AND gate we need A, so we can connect it to A. So that's it. This is the circuit for a 2-to-1 multiplexer. Sometimes we see these with an enable port. So if you see this with an enable port, simply we can add an AND gate here at the output, and then this will become our output Z, and this will be the enable port. So as we see, if E is 0, the output will always be 0, but if E is 1, we will enable this circuit. So we can pass I0 or I1 to the output. So this was a quick introduction about a multiplexer and how we can draw the circuit for 2-to-1 multiplexer and how we can derive the truth table for it. In the next video, we can see how we can draw the truth table for 4-to-1 multiplexer, then 8-to-1 multiplexer, and how we can also design a circuit for each one. I hope this was helpful. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.